Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. We are doing hydrocarbons, and today's topic is preparation and properties of alkanes. So, petroleum and natural gas are the main sources of alkanes, but they can be obtained from number one, unsaturated hydrocarbons. So, dihydrogen adds to unsaturated hydrocarbons in the presence of platinum, palladium, or nickel as catalyst to form alkanes, and this process is called hydrogenation. A bond breaks from here, one hydrogen is added here and another to this carbon atom. So we get CH3, single bond CH3. Similarly, on addition to propene, we get propane. On addition to propyne, two hydrogen molecules, two bonds will break, two hydrogen molecules will be added to form propane. The catalyst, the metal, acts as a catalyst by providing surface for adsorption of hydrogen gas, thereby activating the hydrogen-hydrogen bond. So on one valency freed hydrogen is added, on the other the alkene molecule is added. So this facilitates the approach of the reactant molecules to one another and thereby makes the reaction fast. So first is by hydrogenation. Second method, we can also prepare alkanes from alkyl halides. From alkyl halides we can carry out its reduction with zinc and dilute HCl. So when haloalkanes or alkyl halides are reacted with hydrogen in presence of zinc and acid, the halogen of alkyl halide and hydrogen atom will combine to form HCl, and the other H atom gets attached. It is substituted by H to form alkane. Similarly, chloroethane will form ethane plus HCl. Again, Cl combines with H to form HCl. Similarly, 1-chloropropane will form propane on reaction with zinc, acid and hydrogen. Alkyl halides on treatment with sodium metal in dry ethereal solution. Here alkanes, this reaction is known as Wood's reaction. The ethereal solution should be free from moisture. The two molecules of alkyl halide will react with sodium in presence of dry ether. Na and Br will combine to form NaBr. Similarly, this another Na will combine with Br of this molecule to form NaBr, and this CH3 will join up with this CH3 to form ethane with even number of carbon atoms. So symmetrical alkanes are formed. The limitation of this reaction is also that only symmetrical alkanes can be formed. Ethyl bromide with sodium in presence of dry ether will form 4-carbon alkane, butane. So you see, if we react an alkyl halide with 1 carbon, we get an alkane of 2 carbons. If we join an alkyl halide of 2 carbons, we get an alkane of 4 carbons, and so on. If two different alkyl halides are taken, mixtures of alkanes will be formed. Third is from carboxylic acids. So carboxylic acids, sodium salt of carboxylic acid is heated in presence of soda lime. Soda lime is a 1:1 mixture of sodium hydroxide and calcium oxide. Soda word is for NaOH, lime is for CaO. It is heated with soda lime. The NaCO part of sodium ethanoate and NaO part of NaOH will combine to form Na2CO3, and H gets attached to this group to form alkane. So alkane with 1 carbon less is formed along with sodium carbonate. So this method is called decarboxylation reaction. So once again, sodium salts of carboxylic acids on heating with soda lime, that is mixture of sodium hydroxide and calcium oxide, will give alkanes containing one carbon less than the carboxylic acid. And the process of elimination of carbon dioxide is called decarboxylation. So if we have to form propane, then we will take a sodium salt of acid of 4 carbon atoms, because 1 carbon less alkane is prepared. So CH3, CH2, CH2, COO and A will combine with soda lime, and Na2CO3 will be formed, and this will combine with this to form propane. Kolb's electrolytic method. In this we carry out electrolysis of aqueous solution of sodium or potassium salt of carboxylic acid. So on electrolysis, an alkane will be formed with even number of carbon atoms. For example, if we are using sodium acetate and we are carrying electrolysis of aqueous solution of sodium acetate, then 2 minus 1 is methyl. Methyl joining with methyl will make ethane. So ethane will be formed. Along with that, carbon dioxide gas is evolved, NaOH is formed, and hydrogen gas is also formed. So on passing current, the sodium acetate will break up into its ions, acetate ions and sodium ions. Now in an electrolytic tank, negatively charged ions will go to the positively charged terminal, whereas the positively charged ions will go to the negatively charged terminal. So as it is an aqueous solution, we have 2 negative ions, OH negative and acetate ions, and 2 positive ions, Na positive and H plus ions. So at anode, there will be oxidation. Acetate ions will migrate to the anode and lose their electrons to form acetate free radical. Now this is unstable, so it will decompose to give off carbon dioxide gas, and methyl free radical is formed. So 2 acetate molecules will give 2 carbon dioxide and 2 methyl radicals will be formed. These methyl radicals are very reactive and combine with each other. One electron will form a bond, single bond between the methyls, and ethane will be formed. At anode, ethane is released. So water on taking up electron will form hydrogen. 2 such hydrogens will combine to form hydrogen gas. Hydroxide ion will be also produced. This hydroxide ion and this sodium ion will combine to form NaOH. So overall, the products will be ethane, carbon dioxide, NaOH and hydrogen. So the limitation of this reaction, Kolb's electrolytic method, this reaction is called Kolb's electrolytic method. Limitation of this reaction is that methane cannot be prepared by this method because it contains only 1 carbon atom, and in this method we prepare alkanes with even number of carbon atoms. Properties of alkanes. First is physical properties. Alkanes are almost non-polar compounds because the bond between the carbon atoms or carbon and hydrogen atom is covalent. It's shared, the electrons are shared equally. So it is non-polar in nature. The carbon and hydrogen have same electronegativity, so electrons are shared equally. So because they are non-polar, they possess weak van der Waals force of attraction. The attraction in non-polar molecules is weak van der Waals forces of attraction. So due to weak forces, the first 4 alkanes containing 1 carbon to 4 carbon atoms, these alkanes are gases. They are gaseous in nature. Alkanes having 5 carbons to 17 carbons, they are liquids. And those alkanes which have 18 carbon atoms or more are solids at 298 Kelvin. There is no color of alkanes, there is no odor. These are colorless and odorless compounds. They are insoluble in water because they are non-polar. By nature, only polar compounds dissolve in polar solvents like water, whereas non-polar compounds like alkanes are soluble in organic solvents. So, non-polar compounds like alkanes will dissolve in organic solvents like benzene, carbon tetrachloride, etc. This solubility equation is according to the famous saying, like dissolves like. Polar compounds will dissolve in polar solvents and non-polar compounds will dissolve in non-polar solvents. Now, petrol is a mixture of hydrocarbons. It is used as a fuel for automobiles and it is also used for dry cleaning. So, grease can be removed by dry cleaning. So, solvent petrol dissolves grease because grease is also made up of non-polar high molecular mass hydrocarbons and petrol is also non-polar, so like dissolves like. Now, boiling point of alkanes, the boiling point otherwise is less. It increases with increase in molecular mass. So, hydrocarbons are generally volatile solvents. The intermolecular force increases with increase in surface area. So, bigger the molecule, more will be the surface area and more will be the boiling point. In case of isomers, the molecular mass is same, but a normal pentane, for example, is a bigger molecule than isopentane, which has a branching, a methyl group at second position. Similarly, neopentane is even smaller in size. It's having more branches and so it's acquiring a spherical shape. So smaller the molecule, less the surface area, less will be the boiling point. So we can see that normal pentane has a boiling point 309 Kelvin. The isopentane has 300.9 Kelvin boiling point and neopentane has only 282.5 Kelvin boiling point. So with the increase in number of branched chains, the molecule attains the shape of a sphere and this results in a smaller surface area and weaker intermolecular force of attraction, which are overcome at relatively lower temperature. So the boiling point is less. Next is chemical properties of alkanes. So alkanes, as we have done earlier, are generally inert in nature and do not react with acids, bases, oxidizing agents and reducing agents. Only under certain conditions they will undergo the following reactions. First reaction is where the hydrogen atom of the alkane is replaced by some other group, for example, halogen, nitro group or sulfonic acid group. Halogenation takes place either at higher temperatures like 573 Kelvin to 773 Kelvin or in the presence of diffused sunlight or ultraviolet light, which has high energy and can provide the energy needed for breaking of the bonds. Lower alkanes do not undergo nitration and sulfonation reactions, only halogenation reactions. The reactions in which hydrogen of alkanes are substituted are known as substitution reaction. So, when we carry out the halogenation in diffused sunlight or in the presence of ultraviolet radiations, the energy will cause the hydrogen to be replaced by a halogen. So, one H will combine with Cl to form HCl and CH3Cl will be formed. One hydrogen will combine with Cl to form HCl and CH2Cl2 will be formed. Again, it can react with another molecule of chlorine to form CHCl3 and HCl. This again contains one hydrogen. It can react with another molecule of chlorine so to form carbon tetrachloride or tetrachloromethane. The rate of reaction of alkanes with halogens is fluorine are most reactive, than chlorine, than bromine, and than iodine. And alkanes, rate of replacement of hydrogen of alkanes is tertiary will replace more easily than secondary, than primary. Tertiary are most reactive. Out of these four halogens, fluorine is very reactive. The reaction is too violent to be controlled, and iodine is very less reactive. It's very slow, and also the reaction is reversible reaction. So it will be carried out only in presence of oxidizing agents like iodic acid or nitric acid. Because reaction is reversible, the HI formed reacts back with the product to form the reactants. So in order to carry out the reaction in the forward direction, we use these oxidizing agents which will oxidize the HI formed back to iodine and hence make the reaction go in the forward direction. Supposed to proceed by free radical chain mechanism involving 3 steps. First step is initiation. In this step, reaction is initiated by homolysis of chlorine molecule in the presence of sunlight. That is, the bond between the chlorine atoms is broken homolytically into equal parts. Bond contains 2 electrons. 1 electron will go to this atom, another to this. The chlorine free radicals are generated. These are very reactive and will react in the next step, which is called the propagation step, to combine with alkane. So when free radical reacts with alkane, it will break one of the carbon hydrogen bond homolytically again. So one hydrogen with 1 electron and chlorine with 1 electron will form a bond to HCl, and CH3 is left with 1 electron. So methyl free radical is formed. This methyl free radical can further react with an unionized chlorine molecule and again break its bond homolytically. So 1 electron Cl and 1 electron CH3 will combine to form CH3Cl neutral molecule, and 1 Cl with 1 electron, that is chlorine free radical, will be again regenerated. So these steps are repeated again and again, so the reaction proceeds very fast. In addition to this, there are a set of other reactions also which are taking place simultaneously. For example, the methyl chloride formed here can react with another chlorine free radical to form methylene chloride free radical and HCl. Methylene chloride free radical will react with another chlorine molecule to form methylene dichloride and chlorine free radical. So this is the second step, is the propagation step, in which the rate of reaction keeps on increasing. And when the last step is termination, in which all the free radicals combine with each other to form neutral molecules. So reaction will stop after this step, and so it's called the chain termination step. The reaction stops after some time due to consumption, usage of reactants, and or due to following side reactions. So one chlorine free radical can combine with chlorine free radical to form chlorine molecule. Methyl free radical can combine with methyl free radical to form ethane neutral molecule. Methyl free radical can combine with chlorine free radical to form methyl chloride neutral molecule. So as free radicals are consumed, the chain reaction is terminated. But this has combustion. So alkanes, on heating in presence of air or dioxide, will completely get oxidized to form the oxides of carbon and hydrogen, carbon dioxide and water. This reaction proceeds with the evolution of large amount of heat, because large amount of heat is produced. So all hydrocarbons can act as very good fuels. In general, and energy will be produced. All alkanes react with oxygen to form carbon dioxide and water. Due to evolution of large amount of heat, they are used as fuels. But if oxygen is in less amounts, is in insufficient amount, then incomplete combustion occurs and carbon black is formed. This is a useful product. It's used in manufacture of ink, printer ink, black pigments, and as filters. We can also carry out controlled oxidation. So alkanes, when heated with a regulated supply of oxygen or air at high pressure in presence of a suitable catalyst, can give a large range of products. For example, when the catalyst is copper at 523 Kelvin, it will form methanol. Methane will form methanol. With manganese trioxide, methane will form formaldehyde, methanol, and water. With the manganese acetate, ethane will form ethanoic acid and water. Ordinarily, alkanes resist oxidation, but alkanes with tertiary hydrogen atom can be oxidized with KMnO4 to form tertiary alcohol. 2-methyl propane 2-ol will be isomerization. So normal alkanes on being heated with anhydrous aluminum chloride and hydrogen chloride gas will undergo isomerization to form a branched chain alkane. For example, when normal hexane is heated with anhydrous aluminum chloride in presence of hydrogen chloride, mixture of 2-methylpentane and 3-methylpentane and many other such branched compounds may be formed. Aromatization. When straight chain hydrocarbons containing 6 or more carbon atoms are heated at higher temperatures and higher pressure of 10-20 atmosphere in presence of oxides of vanadium or chromium or manganese supported over alumina, the open chain compound gets dehydrogenated and cyclized to form an aromatic compound like benzene or its homologous. If we have a 6-carbon open chain compound, benzene is formed. If we have a 7-carbon compound, toluene C6H5CH3 will be formed. We can also react methane with water in presence of nickel catalyst at a temperature of 1273 Kelvin to form carbon monoxide and hydrogen. This method is used for industrial preparation of hydrogen gas. In pyrolysis, the higher alkanes are heated at high temperature to decompose into a mixture of lower alkanes and alkenes. For example, C6H14 can decompose into C6H12 and hydrogen, C4H8 and C2H6 and C3H6, C2H4 and methane. Pyrolysis of alkane is believed to occur by free radical reaction. For example, preparation of oil gas or petrol gas from kerosene oil proceeds by pyrolysis. The dodecane, a constituent of kerosene oil, when heated in presence of platinum, palladium or nickel catalyst at 973 Kelvin will form a mixture of heptane, pentene and other products. This is pyrolysis. So that's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.